Okay, so we're going to start a new section today, 5.1, Eigenvectors and Eigenvalues. Okay, so I want to start with an example. So here's an example. Let's let A be this matrix 3, 1, negative 2, 0. Okay? And then I'm going to take U to be the vector negative 1, 1. And I'm going to have V be 2, 1. Okay. So let's draw U and V. So U looks something like this, and V looks something like this. Right? Okay, so A is a linear transformation, so A is going to transform these vectors into some other vectors. Right? So A is going to map U into another vector. And what is that vector? Well, you just got to do some multiplication. So you got to figure out what A times U is. So this is equal to 3, 1, negative 2, 0. Multiplied by negative 1, 1. Right? We want to actually compute what this is, right? So you do the row column rule. So you do 3 times negative 1, and then negative 2 times 1, and what do you get? Looks like you get negative 5, right? And then for the other side you get negative 1, because it's negative 1 times 1 plus 1 times 0, right? Okay. So let's draw that. So let's look something like this. Right, so this is going to be 1, 2, 3, 4, 5, and negative 1. So this is A of U. Okay, so you can see that A scales U because it stretches U out, right? You can see that this vector is longer than this vector, right? See that? But it also rotates. Right, so it takes this vector, stretches out it, and then rotates it down, right? So this is what A does. Okay, let's figure out what A does to V. Okay, so what is A times V? Well, it's going to be 3, 1, negative 2, 0 again, times 2, 1. Okay, what happens when you work that out? Well, it's going to be 6 minus 2, which is 4, and then 2 plus 0, so 2, right? So what does that do? Well, let me draw my tick marks here. 1, 2, 3, 4. 1, 2. Looks something like this. Okay, so this is A of V. Okay, so you can see that A scales V, but it doesn't rotate it, right? Okay? So these are two separate scenarios. In one case it rotates it, and the other rotates and scales, in the other case it just scales. Right? What's more is I can actually figure out the factor by which this vector is scaled. So a times v is equal to 4, 2, which is 2 scalar multiplied by 2, 1, and 2, 1 is my original v. Right? So this equation says that A scales V by a factor of 2. Okay, and if my picture were better, you would see that this vector here is twice as long as this one. My picture isn't so good, but that's the idea, is that A just stretches this vector out by 2. Okay? Okay. So when a linear transformation just scales a vector and it doesn't rotate it at all, we say that that vector is an eigenvector of the linear transformation, and the scale factor is called the eigenvalue of that eigenvector. So let me write that down in a definition. So here's the definition. Suppose that A goes from Rn to Rn. So this is a linear transformation. Okay. Okay. If there exists a lambda, okay, so this lambda is a scalar, and a vector such that exactly this happens. So A times V is equal to lambda times V. Okay, so in other words, scales by a factor of lambda with no rotation. Okay, if that happens, we say that V is an eigenvector of my matrix A with eigenvalue lambda. Okay? So that's the definition. So let's review. A general linear transformation will take any vector, and it'll stretch it out and rotate it. Okay? Now, certain special vectors are not rotated at all. They're just scaled. Those special vectors are called eigenvectors. And the corresponding scale factor is called the corresponding eigenvalue.